All right, so Jim runs the Starhaven Observatory, and it's also the spot where our remote station is located roughly, which you can get a demo of over here. And his students are going to do a presentation. So here you go. Hold it. Go for it.
Hello, my name is Kai Hankelman. I'm on our Space Communications Console team at Starhaven Observatory. So here, clicker is going to work. I just tested it. Okay, so see here, this is a Titan I nuclear missile launch console, and we were able to get our hands on one of these, not to launch nukes, but to refurbish it with radio equipment. This model is the black and white model. Ours is the color model, so it's a little different.
Okay, so this is the mess that we gutted out of the original with a lot of blood, sweat, tears, and extra WD-40. This is the console with everything taken out. So this is the original with nothing in it. That was our blank canvas. And here was our first spaceman test with all of the monitors in and the keyboards in the original plate, which we tried to repurpose for our new instruments using a plasma cutter to cut out holes for the new instruments. However, on the last cut, halfway through it, it ran out of charge and we got impatient. So we tried to knock it out with a hammer and it bent up the whole thing. So we kind of just started over with some new plates, which we got from the laser, a little bit water jet cutter. Yeah. It took. Wait. Whoa. You said it worked. Okay. So if you look down at the bottom, those are the plates that we got cut out, and we drilled them out with the drill press.
Just press it and wait because it's a little back.
Okay.
So if it actually stays where I want it to go. So here we're also using Brent up here is the version 1.0 of the upper cabinet. So here we're just figuring out, because not only do we want one row of monitors, one row of instruments, but we wanted to extend it up. So we have 6 monitors and 2 instrument panels. So here's where we were like theorizing that idea. And then over here, we were actually started to make the frame for the upper console. So then here is the finished cut piece we're just discussing. And so we got it all put together. And we have a little shelf, a little small shelf for the monitors to rest on, and a little slot for all of the instruments to go into. So here you can see we're starting to get all of the cutouts that I actually laser cut for the instruments to go into for the second panel. And the monitors just sit in there with gravity, so they rest on the shelf, leaning forwards. So it arcs towards you. It's very cool. It feels like you're piloting a spaceship. So here's with all of the instruments in, minus the bottom cabinet, but at least the top cabinet. So we have all 6 monitors in there and then the upper instruments. And just to get an idea of what it would end up looking like, the finished product in this picture, we ended up just stacking up a bunch of random junk behind those instruments to hold them in place, because you got to start somewhere, and we did not build the shelf yet. But then we built shelves, little stands behind the instruments in order to hold them in place. And then we started talking about doing the same thing for the bottom panel, which proved easier said than done. So we used our biggest radio here. We put that on a shelf, and then on top of our shelf, we put more shelves. So we had like double-decker shelf going on. It was chaotic to hold up all of the other instruments at the correct heights, because not every instrument is the same depth. So we got that. Got all of them put in. Then here is before we painted it with most of the instruments put in. So all the monitors are up there, and all the lower instruments are now put in. This was before we painted it, and the goal was to paint it blue. So here, and then you can see the silver bar right there in the middle. That is our LED light bar. So that will illuminate all of the instruments while you're working, because obviously if you're in a radio observatory, it's going to be dark. and you want to be able to see your instruments, but you don't want it to be like bright white light. So we're using LEDs that you can change the color of. So if you want to adjust the color and brightness for your personal preference, or if you want to have like red lights, orange lights, whatever. So we got it painted, and here is the finished product. So starting from the top, we have our 3 radios on the sides and in the middle, and then from the right we have our alt azimuth control panel. So that allows us to move the antenna however we need. And we also have an XS200 power supply, or power monitor rather, and then the power supply.
And starting on the right from the bottom, we have the kill switch for the entire console. Then we have the power supply for the bottom set of instruments, then the SWR and power meter for software defined radio to its left. And then after that, we have the SWR and power meter for the larger radio that we're going to be using for ISS transmissions and Earth, Moon, Earth.
So here's just a better look at the finished console. It's probably about 6-7 feet tall. It's real big and real heavy. We had to put it on these dollies, and that was a little chaotic to move it around. Yeah, so there's the finished product. Just
Hello, my name is Tristan Martin. I am on the IT group working with the Space Console group a little bit on satellite communication stuff. There you see the rotator that we're going to be using to control the antenna with the alt azimuth rotator that you saw. And here we are testing the software we are going to use with the Space Console. Oh, and here it's all working. We have a demonstration of over there on the table, if you wanted to go look at it. There's again us testing it, more testing. So here's the software that we are using. It is called GPredict. It's useful for tracking satellites and controlling radios and rotators. If you have a rotator, you can hook up to it. It also shows the satellites and the footprints of the satellites there. You can see the dots in the circle. Circle is the footprint, the dot is the current location of the satellite. This software is very useful for helping you plan out your outings if you're doing portable with it. A very useful tool with it is the Sky at a Glance. There's a timeline here with a bunch of the satellites you have on the configured module, which we will get to in just a minute. If you want to download it eventually, here is the website. You can get Windows and Mac on here, and it has some instructions on how to get it for Linux. It is a free software, so that's an upside. So under the preference page here, you can see on the highlighted button there. If you go in there, you can set up a ground station, which is wherever you're going to be operating. You can have multiple of these, which is nice for portable and multiple stations. You can in here set, if you hit the add new at the bottom there, you can make the ground station there by adding a name and a location with longitude and longitude and latitude coordinates for very fine defining. In that same preferences page, if you go back under the interfaces page, you will see a radio and rotator defining. Under here, it is where you would add a radio and rotator for it to, for the software to control. This is the defining radio. So once you click the add new, just like in the ground station, it will pull up this. Here you can set a name, a host, and port, since this is all connected through a serial interface or a CAT interface, depending on what radio you're using. That might be good to know. And then under that's the radio type, whether you're doing receive only or transmit only or duplex, you can set it in there. As well as a push to talk status and a few other things. Once you get that all set up, on the top right there, you will see a button highlighted called radio control. In here, once you click on it, it will open this up. This is where all of the radio control stuff is that helps tune your radio. All of this part needs ham lib, which I will not be going into, but if you want to know a little bit more about it, you can come find me and or ask questions after if we have time. So once you open this up, after you open it up, you can see on the right side there your devices under the settings area. In there, you'll want to set devices for receive or transmit if using two devices. If you're only using one duplex, you just set the one. And then on the left there, you'll want to set your satellite target and your transponder that you'll be trying to talk through or just transmit to. If you want to make sure you have both of these set, if one's not set, you'll have some issues. After you have all of that set, you'll want to hit the track, which will update the downlink and uplink frequencies at the top there. Once you track, you'll want to engage your radio. Once you engage the radio, it will start tuning the radio automatically with the Doppler correction. So you don't have to constantly tune back and forth between the frequencies while it's moving through the sky. That's, wait, so, oh, there is more. Okay, so if you, on the map there, if you right click on one of those yellow dots with the satellites in the circle there, it will show a page, just a pop-up. In there, you'll want to click the satellite info. In there, it will show a bunch of information about the satellite you selected. A lot of information I don't quite know yet. And then on the top there in the middle, you will see another tab called transponders. No. Okay, there we are. In here, it will show all of the transponders you can go through on the, if you're tracking it and engaging your radios, these are all the transponders you'll might look at for figuring out where you want to set the downlink and uplink at. There's a few modes, some of them are voice and CW. That's it for the presentation on G-Predict stuff. Who's Brent, you're next, right?
Yes, I am next, if I believe.
Yeah.
Hello, I am Brent Haney. I am the Director of Experimental Equipment over here at IAS. Here we have a picture of the 285 remote radio station. that you can see there's a demo over there of. There's a much clearer shot of it in its rack. And then we have over here a picture of the antenna, power, and ground part of this. And here we have the rack of what will be going with the hold on a minute. The console. I forgot, I'm sorry. So this is where all the computers and all of the other things we can't fit into it will be going. And then here we have the remote station's antenna with a little sneak peek of our observatory. Here we have the radio that we normally will be using when we meet to monitor the I-70 corridor and the Highway 36. And 76, thank you. Here we have the J-pole that will be operating this station for the next, for however long we have with it. And then, believe. Let's see, don't think it's skipped.
Hello, my name is Coda Both, and I am the field day correspondent for the Starhaven Observatory. In this photo, me and my sister are contacting a lot of people in the United States and Canada. I contacted about 10 people on it.
On side there.
I do not know. This is when we were setting up for the field day. I was help setting up one of our tanks.
This is a picture of the Ruby N0COT radio astronomy building and its very earliest stages. This is on the Starhaven property, and from the framework and roof to the siding and the windows, and missing a picture there. Even some of the electrical, it was built by the students. And we wanted to do something special, so we decided to do a skyscape on the roof, a nighttime skyscape. So we started out by just practicing on cardboard, and then we started painting the 8 4x8 panels to go up on the ceiling. We ended up finding out the panels were 2 feet too long, but we decided to turn them into 2-foot drop downs on the walls. And then we ended up putting up the entire ceiling. And that is a major accomplishment, as we are the art team, not the carpentry team. But we got it. And we clear coated it. And then that's a picture of the completed ceiling. And we haven't gotten the 2-foot drop downs up yet, but we were able to hold a couple of them up to get a good look at what it'll look like in the future. And I think it'll be truly out of this world when it's finished.
Very nice. Who are you?
Oh, I'm Alma Kubri.
Now, here's a picture of my part. So here we have Paul operating a spec amp, currently trying to figure out how we can incorporate this into a future project. And we have me in the red jacket back there, kind of acting like an eye in the sky for him, operating a different remote console way off in the Netherlands, trying to figure out how the spec amp works, how we could probably incorporate it into a project in the future, and seeing, hopefully, if we will be able to do this. And here we have a setup for a experimental analog recording setup with two radios side by side to hopefully work. So the advantages of having analog recording over digital is digital has many quirks that we cannot predict sometimes. Sometimes the software you use will probably have a frequency base that you did not notice, and you can't get those really low frequencies or really high frequencies that you would normally get with a analog recording. And this is why analog would be better for this and why we are using a reel-to-reel. Here's the STID.
So on top of using that reel-to-reel for our radio astronomy setup, this is a helical antenna that we're currently using for our SID project, which stands for Sudden Ionospheric Disturbance. So by show of hands, who knows what sudden ionospheric disturbance is? If you raise your hand, you are a nerd. So pretty much with this, we are able to detect disturbances in the ionosphere because solar flares from the sun and radiation that hits the ionosphere causes disturbances in the ionosphere, which affects radio transmissions. And we are able to pick up these slight disturbances using our helical antenna here. And this project is in collaboration with Stanford University and the US Naval Department. So Stanford University has tasked us with testing not only the helical antenna, but also the differences between this and a spiderweb antenna. So we'll be building this antenna and comparing the differences in our ionospheric monitoring between the two antennas. So this is the data that we are hoping to get for the Navy. So those big spikes there are commands being sent to naval submarines, and we are monitoring how the sun and solar flares impact naval communications. Because obviously you want your naval communications to be as clear as possible, and monitoring how the sun affects those. So with this, we are able to coordinate our radio data with data that we get from the sun and monitoring sunspots, solar flares, all of those things, and monitoring how those affect naval communications. So here is our antenna field that we currently have, and we plan to build a lot more antennas for things like monitoring pulsars, quasars, black holes, all for radio astronomy using our Ruby Payne-Scott building that Ella was showcasing earlier. And on top of this, we're also working on a project called Jove, which will be monitoring radio emissions from the Jupiter atmosphere, because Jupiter actually emits radio signals that we can detect from Earth. So, and we can monitor, so the goal is to monitor these signals and compare that to observational, like optical changes within Jupiter's atmosphere to see if changes in like the storms and hurricanes in the atmosphere on Jupiter have any correlations with these radio signals. So these are a whole bunch of different antennas that we will be testing and using just to compare different, just for the sake of comparing different antennas for all of these different applications.
All right, so with all of this data that we're getting and all of the projects that we're working on, we are planning on sharing most of it with the public. And I actually got to be part of that outreach. A few months ago, I did a presentation for a group of homeschool kids about how, well, mainly about how optical and radio astronomy complement each other by showing us things that the one without the other cannot see. I was pretty proud of my poster board for this presentation. If you look down at the bottom right, I photoshopped 500-meter aperture radio dish in China over the town I was presenting in, and it covered up a good quarter of it, which made a pretty good impact on how big radio astronomy is.
So to finish it all off, and before we go into our questions, we are the International Association for Astronomical Studies from Starhaven Observatory in Strasburg, Colorado. And I'm kind of Joe, Ella, Coda, Brent, and Tristan, all as part of the team, all run by Professor Jim Moravec. Round of applause for Professor Jim Moravec, please. He slowly waddles his way over here.
Oh.
They're still young.
High school.
Uh, Seventh grade to postgraduate. So I am a astrophysicist, and my students will tell you that I'm really a space case. And but I started out 1968 with the Apollo missions. I was a lunar astronomer. And our task with our team was to, in selenology, which is the study of the moon, the geology of the moon, et cetera. We were tasked with the Apollo missions to find safe landing spots on the moon, because we had to impress upon Congress and the astronauts that were going to the moon that there was no RTD coming by in 15 minutes if they have a glitch while they're on the moon. So we had to get them onto the moon and back safely. And so that was how I got started. And 45 and a half years ago, when I was in Boulder, Colorado, I got a job from the university in South Texas, was transferred to the University of Colorado, and I began this program, International Association for Astronomical Studies. Originally, the name was the Association for Scientific Studies, until a mother who was silk screening our new uniform shirts called me one Saturday and said, "Are you meeting on Monday for real?" And I said, "Yes, we are." She says, "You need to take a look at your name and logo. Association for Scientific Studies." Would you believe it took 15 minutes in the planetarium, university? We're looking up at the big screen and there's our logo. It took them 15 minutes before one of the girls says, "Oh my." None of the guys got it. But finally they all picked up on it and said, maybe we need to change the name. And so we became the Association for Astronomical Studies. And so we started getting students from all over the world. Governments were sending high school kids to my program. And it was like a student, a foreign exchange program. You know, they'd be put up in a house here and then go to school and whatnot. But they were primarily studying in the program for a few years. And then they would go back to their country. And so we have students from all over the world that have continued this program, for instance, in China and Switzerland, Sweden, Japan, in countries in South America, some of the countries in Africa. We have a group in Ghana. We have a group in Ethiopia and whatnot. So it's been a lifelong, for 45 and a half years. It's been a wonderful, wonderful journey for me to work with students like these. And the cool thing is, ladies and gentlemen, especially those of you who are any kind of engineer, okay? And you know, the schooling that you had to go through and things like this, and the competition was, from what I was told on the engineering side, from engineering friends of mine, you know, engineering is pretty competitive, especially in aerospace and whatnot. Well, my students, while they were in high school, were getting offered by aerospace industries. We're talking about Ball Aerospace, Lockheed Martin Aerospace, Ford, GE, Raytheon Aerospace. All these companies were looking at my students and saying, hey, we want to give you an internship. And that internship included not only a salary, but it included their college and room and board paid for.
Wow.
And so this has been going on, and even just recently with some of our graduates, one of our graduates was hired by NOAA in Boulder in the engineering department out of high school.
Wow.
Now, these are not all straight A students. They're not all what we call prodigies and geniuses. But these students have found a safe haven. They have found a place that they can just be themselves and just tinker with the things they love to do in science. Our art team, in fact, does more than just art. In fact, our young lady here, Ella, is interested in tinkering with antenna systems. She likes building them. And we have an aviation young lady here, Coda, and she also likes to talk on the radio. But one of our young men, Kai, raise your hand. Okay, good. Kai, summer was given an internship at NASA in Houston at the Johnson Space Center.
Wow.
And he and his team, we just found out, have been invited to speak at a major conference in San Francisco. Yay, and we have Brent, who is one of our college students. He came to us as a high schooler, but he is now in college, and he is one of our adult mentors. And so the program itself is geared to be hands-on, and you've all heard the code word STEM or STEAM, right? The problem that we have in public schools with STEM or STEAM is that it's out of a textbook 90% of the time. Aurora Public Schools have closed down many of their STEM schools because they just did not have the impetus and the staff knowledge, the educators were not trained in how to do hands-on. Our young educators today are told to open the book and here is what you're going to do day by day. Here's what you're going to say day by day. Everything is texted. Everything texted not as thumb text, but in textbook, okay? Their STEM clubs are reading textbooks. They're not doing hands-on experimentation, things like this. In the past years, our group, their predecessors, actually constructed on a challenge from Goddard Space Center in Maryland to try to figure out how to refuel spacecraft in 0G. Okay? And the scientists, the engineers there at Goddard had been trying to do this for 2 years. One of my girls was sent there as an intern, and she told the old guys, why don't you give my group a challenge back in Colorado? They said, a bunch of kids, we've been trying to do this for 2 years, and we are IEEEs and everything else. And guess what? Creation, now this is at Bojo's Pizza down on Colorado Boulevard. Design, created, designed, constructed, tested at Lockheed Martin, delivered to Cape Canaveral in 6 weeks. Wow. The test package. Amazing. So NASA sent the kids and their parents, billeted them on Cocoa Beach, and they had to be in the command center, and they had to work with the astronauts. Oh, wow. On board STS-47. And they had to work with them and teach them how to use the package. The students had to write the book. And the book, by the way, you know those great file cabinets in that back room? The book is in there for you guys. And anyway, they wrote the manual. So after the launch, at the time that they were supposed to turn the equipment on and test it and all this, they had a bunch of Japanese reporters. And they were there in the visitors room looking down, and the kids were there, not the parents. The parents were also in the room. And the Japanese were going, what are these kids doing there? Well, they're guiding the astronauts. That's their package. And they went, this is an American joke, isn't it? You're joking us. No. So, no, we're not. That's their package. And they are directing its operation from the command center here. And by the way, it was successful. We have, over the years, many, many successes. Have any of you ever heard of chilling your radio systems? We do this in radio astronomy. Chilling the systems to get the noise floor down on your equipment. Okay? Usually it was chilling the equipment in some fashion or another. So what we had to do was to figure out, all right, what happens, a question came up, what happens if we chill the transmission line? And so what did they do? They got their antenna out, they got their radio and their meters, and they had the transmission line, and they took a 12-inch strip of plastic. King Soopers donated 40 pounds of dry ice. They crunched it all up, filled the plastic, duct taped it up, and their systems went, the needles went down. Okay? Now in radio astronomy at the NRAO, the National Radio Astronomy Observatories, for which these students work along with other agencies, we're doing that now with liquid helium being piped through our transmission lines. And it works really well. So this started because of our group. And so it's been quite a good time for me. And people have asked me, why am I not retired? They are not. They're the reason why I'm not retired. And their parents. I can't do it without the parent support and whatnot. And I have two people right here. There's John, and there's Mike. And they are two of our mentors. And we have Nikki, Mike's wife over there, who helps out. And because she knows how to connect electrical stuff together without blowing the building up. So anyway, but anyway, it's been quite a ride, and so we have some really cool stuff happening. We are contracted. Like I said, I'm still in research, And these are listed by NASA, Department of Defense, and Stanford and Caltech as research associates. They are on the record as research associates. So anyway, ladies and gentlemen, we thank you.